In our previous video, we were looking at cluster analysis methods, k-means, and hierarchical models, agglomerative clustering. In this last video on cluster analysis, we're going to look at DBSCAN. So how does DBSCAN work? So DBSCAN stands for Density-Based Spatial Clustering with Noise. It's an alternative towards agglomerative clustering or hierarchical clustering because it also deals better with noise than some of the other methods. When you do a DBSCAN, you don't have to set the number of clusters like you do with the hierarchical method or with the k-means clustering. Instead, clusters are based on the density of data points. So it's identifying what's a cluster by looking at where does the data kind of congregate, and then as the data tapers off and there's more empty space, then that kind of ends the edges of the cluster. So when you do DBSCAN, you are defining the minimum number of data points in order for something to be considered to be labeled a cluster. Okay. Now, when you do DBSCAN, you're going to specify the EPS and the minimum samples. So EPS is how close the data points should be to each other to be considered to be part of a cluster. And the minimum sample is the minimum number of data points before it identifies it as a cluster. Okay, we'll come back to this slide in a minute. But so if we think about this here, here's our data points. We're specifying our EPS, how close the points should be to be part of the cluster. So if we're specifying our EPS here, and here's the length in order to be part of the cluster, as we sweep around, all of these would be included in here. And then we get to, that would mean that this blue point here would be part of the cluster. And so then we're looking at the blue point here, and we're looking at how far away it is from others to catch now this purple one inside the cluster. We look at this green point here. Notice this green point is far enough away from these data points. It's outside of this EPS, so it is not part of this cluster. It's also not part of this cluster. And so the green point, which you can't see because, my head's covering it up, it's far enough away. Just try to move my head for a second. It's far enough away from everything that it's actually not defined as being in any cluster. Okay, and so we use DBSCAN often in terms of finding outliers, those that don't fit into any cluster. Now, the methods we were using before, the scores that we were using to assess the different models, again, we cannot use that to compare like DBSCAN to k-means to hierarchical. We can only use that within a method. And when it comes to those scores, they measure how close data points are from each other and how far those data points are from the center of the cluster. So those scoring methods we used before, we can't use them with DBSCAN at all, okay? All right, so what we will do though is we will look at, come on. We will look at our decisions of choosing our EPS, how close the points should be to each other to be part of a cluster. So we'll look at the EPS in a graph like this, and kind of similar to that elbow method we had with k-means, we're looking for the corner of the elbow. In this case, rather than looking at the end of the elbow, though, we're actually looking for the corner. So when we look at this, as we see here as we go across, that our EPS should probably be somewhere around 0.15. It would be appropriate. So we're actually looking for the edge of the elbow as opposed to when the elbow method was looking for the end of it. Okay. When it comes to minimum samples and how many minimum samples you should have, remember the minimum sample is the minimum number of data points before it declares that it is a cluster. Your general rule of thumb is that it should be 2 times the number of variables used to create it. So in a number of the examples we've been looking at, when we looked at, for example, inclusivity and safety are 2 variables there, right? We would do 2 times that. Or if we are looking at our database where we had, what was the other sample? The other example we were looking at? Oh, size of the contract and size of the company. Again, 2 variables. So our minimum sample would be 4, 2 times that. If you have very noisy data, a lot of extra randomness in the data, so the more noisy it is, the larger that you should make that minimum sample. So start with 2 times the number of variables, bump it up a little bit if you are having noise in your data set. All right, so let's practice some DBSCAN. Just a reminder, in case you forgot in the last 50 other videos, or maybe this is your first one. Go to drstephpowers.github.io/BIA. We are working through the cluster analysis Python workbook that you can find here under chapter 9. We're doing cluster analysis under predictive analytics because if we can identify cohorts, we can then predict how people or events are going to behave because they are likely going to behave like others in their cohort. And so we're putting it here under predictive analytics. But again, these methods can be in different analytics methods depending on how you apply them. Cluster analysis and the DBSCAN method are unsupervised learning, unsupervised machine learning, because they do not have labeled data. We don't know who the groups are, so we're exploring and trying to find those groups. All right, let's go into our data set here. We're going to use data frame 3. So that means that don't forget to link to your Google Drive. Data frame 3 here is the customer relationship management data set, the CRM clean. So make sure you grab it here from the left, put it into your Google Drive, and link together your workbook and the Google Drive. All right, so we're looking at our customer relationship management database. We're going to do DBSCAN. We are going to use our k-nearest neighbors. The k-nearest neighbors is going to help us in terms of finding the appropriate hyperparameters. And then we'll actually use DBSCAN here for our cluster analysis. We're also going to graph, so import matplotlib.pyplot_splt. So from sklearn.neighbors, import nearest neighbors, import matplotlib.pyplot. From sklearn.cluster, we're going to import DBSCAN. For DBSCAN, we need to standardize the data, so we're going to do sklearn.preprocessing import standard scalar. It is a distance-based approach like the k-nearest neighbors, so you're standardizing. All right, we're going to take our data X. We're going to turn it into an array. Here we're using question 4, which is the dollar value of the contract, and question 2, which is the company's revenue. So we're going to convert X into an array, and then we are going to take standard scalar and fit transform, so we're standardizing. This is essentially the equivalent to what we did in our previous video when we were making our radar plot. If you'll recall, we did this here where we said define standard column and then column minus column mean divided by column standard deviation. This standard scalar, it's doing the exact same thing. The difference here is we wanted to apply this to each column in our table, so we had to create this function. When you are doing it in machine learning context here, we're doing it with our algorithm, then we can just use sklearn.preprocessing import standard scalar. And since it's already in an array format, we can just do standard scalar fit transform to our X to prep it for our machine learning process. So except we had to do it our own previously because we weren't dealing with an array there. All right, standardize. Now we're going to use k-nearest neighbors. We'll start with the nearest neighbors. We'll say 4 and fit that, okay? And then have it output the distances and indices. We're trying to get this graph here to help us figure out the EPS. So we use the nearest neighbors approach. And our nearest neighbors here, we're going to start with looking at it with 4. And we're using that 4 with the k-nearest neighbors because we have 2 variables in our set here, and 2 times 2 is 4. So this n nearest neighbors that we see here is going to be that minimum samples number as well. So we'll run this, have it pull out the distances and the indices. And then what we're going to do is we're going to sort those distances. That's what this part is here using NumPy, and then plot that. So this is all to create this image here to help us figure out what that EPS is. And just recall from our discussion a couple seconds ago, our EPS is how close the points should be to each other to be part of the cluster. So we're looking for this graph here by using that k nearest neighbors. So we're looking for the turn, the elbow in it, and as we said previously, that's about 0.15. So what that means then is when we do our DBSCAN, we'll do an EPS of 0.15, and we had 2 variables, and so we'll do our minimum sample 4. So that same minimum sample 4 is the nearest neighbor 4 too. Okay, then we're going to fit it and call the labels and get those output labeled values. Because we only have 2 variables here, we can plot it with the scatter plot and see what it looks like. This is the same data we've been using for all the others, so we might as well take a look at how it looks compared to the others. So again, if we're doing the scatter plot from Seaborn, import scatter plot, import matplotlib as MPL. Don't ask me why that there's an extra D there. MPL. Import matplotlib.pyplot as PLT. And then we're going to use that MPL in order to create the size of the dots being 10. And then we're going to plot our scatter plot. Key here is that hue is going to be that CL, those cluster labels. And let's run that. So the x-axis is the projected value of contract. The y-axis is the company revenue. We've told it to put on the right our legend. And our legend here, this tells us that because this number is greater than 1, it's to the right. And because it's greater than 1 here, it's slightly up. We could shift this more so it's not sitting on top of the graph. There you go, so you can shift it over. Okay, let's look at the labeling here. So we can see this group here clearly labeled. That makes sense. Notice with these others here that what we have is we have a group, we have a group, we have a group, and then you see all these blue ones that say -1. Those are the ones it's identifying as an outlier. So it's a little too far away to be part of the gray group, little too far away to be part of the purple group or the brown group. So all the ones that are labeled -1 do not have a cluster. So now that we know how the DBSCAN process works, let's try applying it to our e-commerce data set. So this e-commerce data set from Kaggle, so just a reminder here, if you're looking for the data set, you'll find it here on the left, e-commerce customers, a CSV file. So we need to do pd.read_CSV, e-commerce customers. And if you're putting that in your Google Drive, make sure you've linked to your Google Drive to allow for that import. So let's load in that e-commerce head. And if, like me, you've loaded it previously, so you have the previous label in there, we'll ignore that label for now because we need our label from our DBSCAN as opposed to the label that we've just given it from the k-means approach. So let's create an array using NumPy. And we're going to take our average session length, our time on app, time on website, length of membership, yearly amount spent. All of those are going to be variables that we're going to use to do our cluster analysis here. So we'll call this X. And we will do standard scalar fit transform as we mentioned in our previous videos. Here we're standardizing anytime we're doing the k nearest neighbors in the classification methods, or when we are doing our DBSCAN, we need to do the standardization here. Okay, so what we're going to do is we're going to say first, how many variables have we included? 1, 2, 3, 4, 5. So our n nearest neighbors is 5 times 2, so that's going to be 10. We're going to use the nearest neighbors distances and indices that it provides to figure out the appropriate EPS. So let us do our nearest neighbors. We are then going to have it sort the distances, and then it's going to plot that information. And so we are then looking for the elbow. We're looking for the turn here. And so we're looking about what? About 1 here. So let's go with an EPS of 1. So let's do a DBSCAN. EPS equals 1, minimum samples 10, dbs.fit, okay? And we're going to have it create the labels. Notice here we have -1 and zeros. Okay. Now, what we learned from this e-commerce data previously is that really the most relevant of those variables was the length of membership and the yearly amount spent. So let's actually create that plot with length of membership and yearly amount spent, and we'll put in the labels we just got from DBSCAN. So from Seaborn, import scatterplot, import matplotlib as MPL for the big dots, import matplotlib.pyplot as PLT for our graph, and we're using length of membership and yearly amount spent as our X and Y, and we're color coding based on those DBSCAN labels. So this little helps us visualize what this list is here. And what you see is that first we didn't specify the location of the legend, so we'll put it wherever it wants, as opposed to here on the right where we've been forcing it in the past. And so what you see here is that we have the zeros, so we have a cluster, and then you have the blue, -1. So here what this is showing you if you use DBSCAN for this particular data set is that it is not clearly not identifying multiple clusters. It's saying we have one cluster and then we have outliers. And so DBSCAN can be used to find anomalies or outliers because it's saying the typical values all fall right in here. And so this here out in the blue and this here out in the blue, these are extreme values and they're not consistent with everyone else. So for this purpose, as we see here, we could use DBSCAN to say, okay, well, these people are not consistent with everyone else. So perhaps there is an issue here. And so we can use DBSCAN to help us find anomalies or outliers, things that maybe shouldn't be happening, trouble or problematic issues, things that should be flagged as not being the norm. If we were to look at, let's say, time on app and time on website, so all we're doing is changing the two variables, we can get a better idea of the anomalies here. The blue are the ones that are not classified in a cluster, and then the orange is that single cluster. So you can see out here on the fringes, those who spend a lot of time on the website, that is not part of this kind of center core. So we can use DBSCAN to identify those items that don't quite fit in the cluster. So we have the typical and then the atypical. We can use DBSCAN to help identify the ones that are not typical.